right, good morning, everyone. Thank you all for joining our webinar. We have David McNichol here with Delta Computer Systems to present for you guys. Just a couple of things. Please note that you are in listen-only mode, so if a question does come up during the presentation, please type it in the question chat feature, and we will get to those questions at the end of the presentation. So, David, I'm going to go ahead and let you take it over from here.
Thanks, Jamie. Yeah, so this webinar is going to be focusing on the misconception that hydraulics are slow and old-fashioned. My name is David McNichol. I'm an application engineer with Delta Computer Systems. I've been working with Delta for just over 4 years, seen many applications, have done a lot of field support, and if you guys call into Delta for some help or send us an email, there's a high likelihood that you'll be talking with me. So speed plus precision is controllability. All right, it's fairly easy to have a high-speed application, and it's fairly easy to have a high-precision application. But to have them both together, you need a great deal of controllability, and that's where the Delta RMC comes in. With our RMC, we do high-precision position control and also high-precision, high-speed force control. Here's a list of a few applications. If any one of these applications rings true and you'd like to get a little bit more information, feel free to reach out to GCC or to Delta. We've got more purpose-built webinars that just dive a bit deeper into each of these applications, but the purpose of this is just a brief overview and really more of an introduction to each of these applications. Presses are one of the applications that we do a great deal of work with. Having that high precision position control and force control is a great tool. We'll get to see that here as we continue through this webinar. Simple machines are another area where high precision and controllability are actually extremely important. I've got a few examples on a live system here that I'll be able to show as we continue through here. Another application that we dive pretty heavily into is the test application. Adaptive cycle control is something that we can do. I'll get into what this looks like, but we're able to look at individual cycles, and based upon your desired peaks and valleys, we're able to actually scale up as we're going through. And then 6 degrees of freedom is another application. This is just a list of a few applications that we've done. There's many more, but here's a great introduction. Communication is also something that's very important to Delta. If you can do the application, it's great, but if you don't have any way to then take that data from our motion controller and put it into something like PLC or to LabVIEW, sometimes it doesn't really have as much use. So we've also got great examples built for communicating with PLCs, whether it's Siemens, Allen Bradley, many others, and other protocols as well, like LabVIEW or MATLAB, and I'll demonstrate our LabVIEW example here as we go through. We're also going to talk a little bit about system design and just what Delta recommends. Keeping things simple is always easiest. We'll talk a little bit about the do's and don'ts of our hydraulic design as well, and what we found to work best. So I've got a live example here. I've got a cylinder set up with a high precision, good quality servo proportional valve, and I've also got feedback, high precision feedback that we're going to be using for this example. My cylinder is 24 inches long, 24-inch stroke. I've got 2-inch bore here, 26 gallon per minute valve, a 1 micrometer transducer. Now, with this setup, I can achieve very fast motion, about 35 inches per second is as quickly as I can go, and I'm able to hold position within a thousandth of an inch. I'll show you that here in a second, but just with this setup here, we're able to hold a great deal of precision. We're able to get there very quickly. We're also able to track motion within about 1/100 of an inch. Again, this is very application specific. With our setup here, this is what we're able to do. So without further ado, let me jump to our live system, and I'll give you guys an introduction here. Okay. Now, this is RMC Tools. This is our software that we use with our motion controller. If you're not familiar with it, it's a free software package that comes along with an RMC controller. Right now, I'm trending a plot. This is giving me real-time data. You can see below my software here, I've got physical cylinder. This is what we're going to be moving. Now, I have a few hotkeys set up. I'm going to press 1, and we'll be able to see what happens here. I'm going to be doing a move to a position of 18. Okay, so you saw the cylinder jump out here, and I can see my move that took place here as well. So this move right here, I can see as I'm going, I'm holding with a great deal of precision. Even while I'm traveling in this move, 20 inches per second, I'm still holding within about a thousandth of an inch, really. You can see my actual position is 12.220, and my target is 12.220, and my actual is 12.219. So we're holding a great deal of precision here. And I can see kind of settling there a little bit, but if I trend my plot here, I can see that I'm just jumping back and forth about a thousandth of an inch. I go up to 18.001, and I go down to 19 or 17.999. So I'm holding very steady. You can see, you can't even really see that thousandth of an inch here on the cylinder itself. Okay. Now I can do another move, and this is just all built into Delta. We've got a very nice set of commands here. This is our basic move command. I choose a position, a speed, an acceleration, and a deceleration. And this is all scaled in inches right now. So I could, for instance, say I'd like to move to a position of 2. Now sending that command, you can see that we've generated a profile here as well. This light blue line is my target position, and the red line is my actual position. I can hide actual, and I can see that they're just right on top of each other. I'm tracking very well. This is a high precision setup here. Okay, let me jump back to my slideshow. Now you might say, well, what if my machine doesn't really require high precision? Maybe it's something that doesn't need to track within a thousandth of an inch. Well, high precision and controllability can still be extremely important. One of the benefits of having controllability is that you are able to eliminate pressure spikes. These pressure spikes and shocks can really put a lot of wear on your system. I'm going to demonstrate that here in just a minute. But having these spikes eliminated is going to give you a much greater lifetime on your feedback, right, on your transducer, on your valves, on your cylinders. Everything's just going to last longer when you have high precision and controllability. The other thing is you're going to have improved quality, and you're going to reduce waste. Much easier to improve the quality, make sure that things are consistent with this controllability, reduce waste, only go as quickly as you need to. You know exactly how much pressure you need. It just makes things a whole lot easier in your system. So here's a great example of a simple machine that doesn't really require precision, but a high degree of controllability is still very beneficial. This is an application that we were just involved with recently. This is the mining application where there's coal on a conveyor belt, and there's a And again, it's a very simple application, right? Just having two bang bang valves on here, what this does is we start to see pressure spikes. Things start to wear out. For this particular application, every 6 months or so, they were having to replace components because there's just so much force constantly being seen by these cylinders and these valves and these transducers. We see cavitation as well. With the pressure spikes, when that pressure goes below zero, we'll start to see cavitation, little air pockets inside the hydraulic fluid, and that's what can really start to wear things down. Okay. Now, if we instead make these servo proportional valves, we can have gentle motion, we can extend the life. Sensors are going to last a lot longer. That's one thing that really will start to wear out quickly. But the entire life of the machine is just going to be much better. You're going to be replacing parts at a much lower frequency when you have gentle motion. Okay. See what that looks like here on our system. So again, I'm going to be using my live system here. I'm going to trend my axis 0. Right now, I'm trending. I can see I've still got my target and my actual position, the blue and that red line there. I also have channel A pressure and channel B pressure. So I have pressure transducers on either end of my cylinder, so I'm able to see what the pressure spikes are going to look like here. So first, what I'd like to do is run my pressure spikes program here. Now I'm going to briefly go through the logic. You'll see that Delta has a very nice approach for actually setting up this logic. With the setup that we have here, you're able to achieve whatever it is you'd like to in your system very quickly, and even better than the speed, it's very easy to troubleshoot through, understand exactly what's going on, and if there's a problem in the system, we're able to diagnose it very quickly. Okay, so the first step that I have here is I'm going to move back to a position of 2. So I think my cylinder is fairly close to there right now. Actually, it might even be exactly there. But I just want to start at the beginning. And my purpose with this example is demonstrating what it would look like if we were to do something like this in open loop control with a bang-bang valve, basically demonstrating what this conveyor system that we just looked like had before the Delta RMC was put on. It's a direct output of 100%, right? I'm opening up my valve, this 100%, as high as it goes. I wait until I get to a position past 10, and then I close my valve, right? So might not need high precision. We probably aren't going to get within 1/1000th of an inch here, but we might still get, within half an inch or so, and maybe for this application, it's not a huge deal. Let me show you what this looks like. One quick thing I want to mention here, I'm going through this very quickly. I know that there's a lot of information here. Again, if you would like to dive deeper into any one of these topics, please reach out to GCC. They're great. They can really help you guys out, and we've got a whole lot more information on any one of these individual topics. Okay, so let's see what this program looks like here. All right. So I'm going to look here at my actual, we'll first look at our actual position, see what this looks like. So my actual position, this red line here, starts at a position of 2, and we build up to a position a little bit past 10. We're going to about 10.5 inches here, so maybe a 3 application, that's fine. My control output, it's just ramping right up, right? This is open loop control output, so there's not really any controllability here. Now, when I look at my pressures, I really get a better picture of what's going on in the system. You can see the orange line here is my pressure on port B, and the gray line here is my pressure on port A. It's very noisy, especially at the end in the beginning here. There's just large spikes, really, especially at the end here. This isn't going to be good for the system. I don't know if you were able to hear it through my mic, but very loud, very noisy. There's a lot of shock here, and it's just not really what you'd want if you're trying to prolong the life of your components. Okay, so that's without controllability. Let me show you another program, and this would be more of Delta's approach. Again, I'm just moving to the beginning here. You can kind of disregard this step. This is really the step that we care about and the step that's going to be achieving exactly what we did in OpenLoop before. I'm, again, just using a move absolute command, moving to a position of 10. This way I can specify my speed. In this case, I'd like to move at 20 inches per second with an acceleration of 100 inches per second squared and a deceleration of 100 inches per second squared. Now, after this, my program ends, and the Delta RMC is going to make sure that we maintain this position of 10 inches. So very simple, easy to set up, and we're going to get a great deal of controllability from this setup here. So let's see the difference. So this section of my plot here is what I really care about. I'm going to create a trim plot really quick. Now, we'll get rid of the other items. At first, my motion profile doesn't look all that different from the one before. The big change here is that I actually get to 10 inches rather than 10.5. But again, we're going to say for this application, 10 or 10.5 doesn't matter quite as much. But if I look at my control output, you can see it's a much smoother ramp, right? It's not that violent jump up and violent jump down. If I look at my pressure, you can also see this is a much smoother pressure profile on both the A port and the B port. Something like this, you're not going to see, a large damage to your controller because we're able to control these accelerations. We're able to reduce them and get them to a point where this system is just going to have a much longer life. Okay. So let's jump back to our slideshow. So here's a few common position control features. Seen a little bit of what we can do, motion profiles. We could have much longer, much more involved programs, user programs that you saw. I demonstrated just a few smaller user programs, but we can get much larger and much more involved programs. Curves, I'll demonstrate this here in just a minute, but we can actually plot points, and we can then have the controller follow those points and follow a profile. A good example of someone using our curves is USNR. If you haven't heard of them, they're the world's largest sawmill machine manufacturer. They love Delta Control products. They've been using our products and our curves in specific for curve sawing. It's a great tool and just really useful. You'll get to see it here in a second. We can do gearing as well. So this is something I didn't talk about before, but that whole machine had 2 cylinders. And some of you were probably wondering, well, how do you keep those 2 cylinders level? How do you make sure that things aren't tweaking and we're not just relying on mechanical guides to keep things where they need to be? We can electronically gear axes together, and again, we can do this with a great deal of precision, a thousandth of an inch with the setup that we have right now, even less if you're using other setups. Motion sequences, again, we can set up these sequences in user programs. We can have programs one linked to the next. I've got some great examples I'll show you here in just a minute on these motion sequences. And advanced logic. So if, say, you've got a application where our standard commands, well, for one reason or another, they just don't quite exactly fit what you need to do, you can even do advanced logic and kind of more custom programming inside our user program. So very user-friendly for basic things, but still able to achieve things when you have a much more difficult I'm going to jump back to RMC tools, and I'll quickly show you an example of our curves here. Again, since we don't have a ton of time today, this is just a brief overview. If you'd like to see more, go ahead, reach out. Delta also has a large library of webinars where we go more in depth on each of these topics. Okay, so this is my curve tool in RMC tools. I've got a few points that are already set up. Generally, my x-axis here is going to be time, and my y-axis is going to be position. We can change these around a bit if you need, but just imagine this axis here is time, and this axis here is position. If I were to run this curve, after 1 second, my axis would be here, right? This would be about 2.3 inches, and I would continue to climb up, and I could follow this profile. Now, maybe this is for a curve saw, and this is being generated from an outside source, so you don't want to change something. We can leave it exactly like it is, and we can run it. But we also are heavily involved in the entertainment industry, and a lot of times they like to use curves for animation profiles. And there they might want to add another point. So I can double-click anywhere. I can add another point. I can drag these points. I can move them. It's very easy to move these along here. I can add more points just like this. I can enter them in, and I can copy and paste entire profiles like this from an Excel worksheet. Say you have 1,000 points and you'd like to bring them all into RMC tools. So it's a very versatile tool. We're able to run these profiles and able to do it no problem at all. Okay, so that's our curves. That's just a brief introduction. Let me jump back here. All right. Now, force control is something that's difficult for a lot of controllers to achieve, and it's an area that Delta really excels in. Now, the hardest part of force control is generally the smooth transition from position to force. This is where a lot of things can go wrong. It's difficult to get a nice smooth transition where you don't push too hard on your part, but in addition to that, that you, at the same time, get up close to your part very quickly. Doing these things together can be a challenge for many controllers. So let me show you our solution for that. Okay. So our Enter Force Control project here, I'm not going to go over it too much. It's a little bit more advanced. I want you to take a brief peek at it here, but I'll show you what we're going to be doing here. Basically, the idea behind this is I'm going to be going quickly up to a position. Then I'm going to be slowing down as I start to get close to my part. Got a speed of 20 here, and then a speed of 1 here. Once I see a little bit of force, I'm going to go into force control. And then for this program, we ramp up and down between two forces. You can do whatever you'd like to with your program. Maybe you hold force, maybe you wait for a time and you retract after that. Many options. Okay. So I'm going to trend this here. Force control. You can see right now my black line is my actual force. My yellow line is my target force. Right now we're not trying to hold force. Instead we're trying to hold position. You can see we're holding within 1/1000th of an inch. We're just free floating. We're not really seeing any force at all. So I'm going to run my Enter Force Control program, and you'll see my cylinder jumps forward quickly, slows down. We make contact. We're controlling very well. We're ramping up and down between a couple forces. Okay, so you can see that there. Right now we're holding force within, looks like here, once we settle down, within 5 or 6 pounds. So fairly precise. If we have a different valve on here, we could even get it more precise, but we can do very high precision force control. So if I analyze my plot here, I can see this blue line here, my velocity. It's gone up very high, gone quickly, and then we've slowed way down. We could probably even reduce this time here if, say, this was an actual production model and you wanted to get quicker cycles, we can reduce this down. But as we get close, we start to see a little bit of force if I zoom in here, and then we go into force control. We start tracking, and we're tracking along with our force control, and we're able to control this very well here. Let me show you this one more time just in case you missed the physical cylinder. Okay, so we're tracking to the beginning. I go quickly up, making it to force control, and that's a very smooth transition into force control here. Okay, so that's one application. Let me show you another. Another application here is going to be presses, right? This is something that Delta does very well. We're heavily involved in the press industry, and there's some unique challenges to the press industry here. So position and force need to be controlled, as we saw before. There's also a synchronization that needs to take place. Now, this synchronization takes place through a program that we have called electronic platen leveling. We can do this from cylinders that are pressing down. We can also do this with press cushions as well. Here's another great little just demonstration. This powder metal pressing, I can see that my powder gets pressed in by my chute here, and then the fingers come up and they press apart. This is another application, again, that requires a lot of synchronization and force and position control, something we do very well. So what I want to do is pull up a quick video, give you guys an idea of what this actually looks like.
The RMC-151 motion controller from Delta Computer Systems offers synchronized position force control on multi-ram presses, where the ram positions must be identical regardless of the load distribution. This two-cylinder press has a very flexible platen. The RMC will keep the platen perfectly level while controlling the total force. The platen moves down in position control, then seamlessly switches to force control and rams the force up and down. The cylinders are staying level with each other, within approximately 0.003 of an inch. With a stiffer load or slower ramps, it is easier to achieve even tighter tolerances. Notice that the load block is not at all centered in the system. This illustrates the ability of the RMC to keep the cylinders synchronized. Let's look at a plot of the motion. The position is red, the desired total force is yellow, and the actual force is black. The press moved in position control, transitioned into force control here, then began ramping the force up and down. Looking at another plot of the force ramping, we see that the skew between the cylinders, shown by the gray line, is 0.002 inches at the cursor. The RMC-151 can handle up to 6 axes of synchronized position force, depending on the feedback signal type. For more details, contact Delta Computer Systems.
Okay, so that was our video. You were able to see there how we do the synchronization. That was a 2-cylinder press. Generally, we're going to be doing the synchronization in something more like a 4-cylinder press. We've done this many times with great results. If you'd like to see some case studies, both Delta or GCC would be able to provide that to you. Okay, so let's move on in our slideshow. We're also very heavily involved in the test industry. Now, here's something that we found Delta has that has been very useful for the test industry in specific. We call this our adaptive adaptive cycle or adaptive amplitude control. We can adapt and control both position and force. We can control amplitude, phase, offset, and this is a very flexible program. Basically, what this does, I spoke about it a little bit in the beginning. What this does is it looks at where your targets are, right? It looks at where is your target peak, where is your target value, for instance, with amplitude control, and cycle to cycle, we actually adjust so that we hit those targets. The reason that we do this is sometimes you've got a testing application where the frequency that you're trying to do things with is just too quick for a traditional PID. And so using this approach, we're able to get very good results. Here's an example of what this looks like. So this blue is my offset here. The green is my peak target, and the black is my valley target, and the red is my position. So even a system that's not really tuned up very well, like this one is on here, you can see the first cycle goes, and then we start to build up higher and higher and higher until we get to a steady state around here where we're hitting our valley, we're hitting our peak, and we're right at the desired offset. So using this approach is a great way to achieve cycle control for a testing application. And it's also very easy to set up. Again, we have these examples readily available. If you'd like one of these examples, just let someone know and we'd be more than happy to provide you with them. But it's very easy. All the programming has already been done. All that's left for you to do is enter in where you'd like your amplitude, offset, and frequency. And the rest has already been taken care of. Another test application is our 6 degree of freedom Stewart platform. This has been very useful in doing vehicle simulations, other things as well. For instance, in the entertainment industry, it's very useful if they say want to connect up a ship or a stage. We're actually involved in a few different movies where they have an entire ship that they were putting on a Stewart platform, and we were controlling it as the actors were doing their thing. Vehicle simulation is another thing that's great with these 6 degree of freedom systems. We're able to gather data, acceleration data from real-world examples, and then we're able to play that back through our 6 degree of freedom system so that the manufacturers can test and make sure that their cars are going to be all right without actually having to drive them. Okay. Now, let me show you a live example of this. I'm going to swap videos here. And this is our mini 6 degree of freedom Stewart platform here. I'm going to flip on the hydraulics. It's going to be a little bit noisy here for just a second. And I've got a second controller here that I'm going to be running our tasks with. The cylinders are a little bit bottomed out, so I'm just going to extend them up here. And let's go ahead and run this. I'll show you the video here in just a second. Just a little pause out here. Let's see if I can just show you one of them. Okay, so this is our 6 degree of freedom system here. You can see it. Let me minimize my screen just a little bit. I'm going to go ahead and start our program here. I've got a little bit of negative over travel. See if I can just expand this a little bit here. See if I can get this running. Okay, here we go. So it was bottomed out at the top, bottomed out at the bottoms. We have some stops set up just for safety. Just wanted to make sure that this is right where it needs to be. This is our 6 degree of freedom system. It's going through a show profile, going through multiple programs here. You can see on the top of my screen, basically go through a number of programs. Go through a circle flat program, a circle tilt in, a circle tilt out. I've got quite a few different programs going on here. But you can see we're controlling this very well, moving really nicely. Again, this is just a demo, but we've got all the code to get this set up. We were actually just talking with a customer not too long ago about how easy this would be to get set up. And since we have all the code built in, really the toughest part is just going to be measuring the distance of where your cylinders connect and making sure that that's entered into the RMC. But everything else is set up, and it's a nice, controllable system. Okay, so I'm going to stop this. And I'm going to turn off my hydraulics here. And we'll just turn off this controller. That's our 6 degree of freedom system here. Okay. I'm going to jump back to our slideshow now. Now, I want to talk a little bit about system design. Position sensor, magnetostricted, high resolution, 1 micrometer SSI. 1 micrometer is a pretty common precision resolution, rather, for SSI transducers. This is a very nice setup and something that we highly recommend you getting if at all possible. High quality linear proportional valve, having this on your system, these two components together is basically what we've been seeing on the live system. The valve mounted directly on the cylinder is an important part of this here. Having this valve mounted directly on the cylinder guarantees that we're not going to have any springiness inside the system. It's going to be much easier to control. It's not going to bounce. If you say have a hose, if it's a long hose in between the valve and the cylinder, that hose is going to act like a spring. It's basically going to expand and retract, and it's going to make the system much more difficult to control. So if you can have hard pipe and your valve mounted directly on the cylinder, that's how you're going to have the best chance of great control. A pump and a tank, these just right to your valve. Sometimes you can have it this simple. If your system allows for this, it's great. It's a nice, easy way. The other thing that we want is to have an accumulator here just to make sure that it's close to your valve and that we're going to be supplying constant pressure. So that's what the accumulator does, right? It basically charges up and it makes sure that you've got this nice, smooth, constant pressure in your system. Okay, and then of course you have the motion controller for the hydraulics. All right, here's some don'ts. Hose between the cylinder and valve. Like I said, that creates springiness in the system, which makes it much more difficult to control. It brings it into what we call a second order system. Long distance between the cylinder and the valve. Again, this is going to provide the springiness to the system. Counterbalance valves, if you can avoid them, we'd recommend it. Some applications it makes sense, but a lot of them, it just makes things very difficult because you're basically trying to control something electronically and hydraulically at the same time. Nonlinear valves, this is another thing that makes things difficult to control. Having a nice linear valve with no deadband is the way to go. It just makes control much easier and you'll be much happier, especially if you need very high precision control. And just avoiding low quality valves is really a must. Analog position sensors, your only option. If it's, say, force control, you don't really have any other option. But if you can, avoiding the analog position sensors is great. Okay, PLC communication. Again, like I mentioned in the beginning, we can communicate with all popular PLCs. We can do this with Profinet, Modbus, Ethernet IP, many different protocols. Lots of data can be exchanged between the motion controller and the PLC. That's no problem on our end. So lots of data, many communication protocols. This is digitalization. Having digitalization is going to allow you to do things like preventative maintenance, improved efficiency, and improved cooperation between your whole system. Many people love the Delta controllers because we're able to gather all this information and give it to them in a meaningful way. Here's a quick example of preventative maintenance. We have our actual position here and our control output here. To see if things are changing mechanically in the system, what we can do is we can actually add basically guides for the control signal. And if this control signal goes beyond these guides, well, you know that something mechanically has changed in the system. And when that happens, maybe you want to try a few more plots and see what's actually going on, just so you can get to the root of the issue. Okay. So why a motion controller compared to a PLC? We have more specific motion control features than a PLC would. A PLC can do some of this. It can't do all of what we are doing here. In some applications, it might make sense to go with a PLC. In most high-precision motion applications, we found our customers to be much happier with the RMC, spend much less time getting things set up, and it's a whole lot easier to troubleshoot when something does go wrong. We've got features rather specifically for hydraulics. That is really Delta's niche, is high precision hydraulic motion control. We do a very good job at it. And when you have a system that is a little bit more difficult to control, we've got much more specific features for doing things such as this. If you'd like to look into that a little bit more, I'd encourage you to reach out. We've got a lot of great examples. You can use smaller PLC as well, so you don't need a massive PLC doing everything. A lot of times people have a much smaller PLC to do the same job that they would if they were trying to have everything in one PLC. Position and forth with the same actuator is nearly impossible with PLC. This is true. It's very, very difficult. We've yet to come across a PLC that can do this position force application well. Here's a brief customer quote. There is no comparison. Our customers really are happy with Delta. Experts in servo hydraulics control. We have more than 35 years of experience. When you have a Delta product, the whole Delta team is there for you. We've got free tech support. We really try to make sure that your application is taken through to completion and that you're happy with the results. And easy to use, powerful motion controllers. Like we've seen here, they're easy to use. They're great controllers. Knowledgeable support. No obsolescence. We make sure that our products are always going to be available for you. Okay. And we can help you design your hydraulic motion control system. Not so much in that we'll give you designs for it, but we do publish a hydraulic design guide. This is a great design guide. It's put together by Peter Natchway, the president here at Delta. He's an extremely knowledgeable individual. He just made it into the Hydraulics Hall of Fame, and he is just really the reason why Delta is where it is today. He has a very in-depth knowledge of hydraulic control. So if you would like this, again, we highly recommend you reach out and ask us for a copy. We'd be happy to provide one. Okay, more information on RMC controllers. If this was just too much information too quickly, don't worry about it. We've got a nice training sequence of videos. It takes about an hour of time, and if you've got a new RMC Tools application, great resource here. Watch through these videos. It'll give you a really nice introduction and overview able to go very quickly, and able to do just a really good job with our motion profiles. Simple system design. It's nice to have electronic controls because you can keep your system much more simple. There's a lot less to go wrong in that case. Fast implementation. We're able to get things up and running quickly, and since we are our niche is hydraulics, we have very much so a purpose-built product that does a really great job getting you up and running as quickly as possible, and adaptable for any application. Okay, well, thank you everyone for attending. Jamie, I'm going to pass it back to you. That's everything I have. I'm not sure if there's any questions.
Yeah, thanks, David. We did have one question come in, and that question is, do you recommend using blocking valves under a servo valve?
In some cases, it can make sense. So with press applications, we've got a few hydraulic schematics where that actually would make sense, but not in every application. I guess what our main thought on that topic would be is make sure that things are safe, right? We don't want to be the safety controller in the last line of defense. So if safety is concerned, sometimes it can make sense to have a setup like that. If you just want, precision control, well, it might not make sense there.
Perfect, thank you. And since we are a little over on time, I'm going to go ahead and close the board, but if questions do come up after the presentation, please feel free to reach out to marketing@gcc-na.com, and we will be more than happy to connect you with David. Other than that, thank you all for joining. David, thanks again for your presentation, and we will talk later.